It's the IoT Security Foundation monthly webinar for February 2026. And if you missed the last edition, IoTSF members can watch the entire recording in the members only area on our members platform, or you can watch one of the two presentations on the IoTSF YouTube channel, that being CRA compliant software development with zero trust attestation. That was with Florian Lekavsky of SignPath last month. Another YouTube video that you can watch features one of today's guests, Stephen Kennedy, presenting NIST standardization of post-quantum cryptography, which is taken from the most recent online meeting of the IoTSF's Quantum Safe IoT Special Interest Group. For those watching live, I'm going to put the links for both of those presentations that I've just mentioned in Zoom chat in just a few moments. But let's get into it. Today, we're going to hear all about quantum safety in IoT. Coming up a bit later, we'll have Stephen Kennedy, but first up is Richard Brooks of IoTSF member Bluemesh Solutions. Richard, the floor is yours, my friend.
Thank you very much, Chris. My name is Richard Brooks. I'm from Bluemesh Solutions. I'm a founder of the company. I'll give you a little bit of backstory. So on the screen right now, you can see a picture of a very large cargo ship, a very large port, and some very large cranes. So a few years ago, 3 years ago, Bluemesh was invited to put sensors, IoT sensors, onto things, and we picked big cranes in the port of Felixstowe. And the point of this was that this was the very first private 5G network in the UK. It was a technology demonstrator. It was part funded by government. We had a nice team of people working on it. Obviously, we had the port because it's there. We had ourselves, Bluemesh. We had Cambridge University. We worked with their team in the engineering department. We also had Hutchinson, who owned 3UK. So they were doing the 3G bit, the 5G bit. And we had Ericsson as well, who set up the network, put the antennas up and backhauled the data. So the project was, well, my part of the project was, put sensors on cranes, and you can probably just about see one with a little red box on the lower image, and then measure on critical parts of the cranes where they vibrate. And if they vibrate a lot, they're probably getting a little bit old and shaky, literally. And if they're not vibrating too much, then they're probably good for a while. We sent the data to Cambridge University. They built digital twins of these cranes, and we could predict then which cranes would need maintenance and which parts of the cranes would need maintenance. Right at the end of the project, we were introduced to a government department who wanted us to test a up and coming new technology called quantum safe encryption. So we worked with a UK company called Arkit for a while, and we partnered with them, and we did some work with their software developer kit, and we created an MQTT data pipe to backhaul data using a quantum encrypted wrapper around the data. Okay, thanks, Steve. So that was the backstory, and that's how we got into the into this particular space, and that's how we got more and more deeply into what is the quantum problem and why is it relevant to both large computer networks, but also why is it relevant to IoT devices. So what is the problem? The problem is that quantum computers, which I'm guessing most people on here have heard of by now, calculate in a different and more powerful way. And rather than having classical zeros and one bits in a gate queuing up and passing through the gate, qubits, which are quantum bits, they combine a 0 and a 1 in the same memory space, which means that as you start to add these twos together, these zeros and these ones, these two spaces, the quantum computer allows exponential scaling of the memory space computational power. And a lot of money and development time has gone into this, as you're probably aware, because you see lots of announcements at the moment. And enough money and enough development has gone in for some of the leading quantum computing companies now to start to discuss there's going to be a breaking point. And the breaking point will be that these computers will probably get powerful enough to start to decrypt some of the common encryption that we're using currently. And there's an estimated date that's kind of flying around in the market at the moment. It's around 2029. It might be around 2030. It might be around 2031, but there seems to be it's coming. Thanks, Steve. The problem of this is that anything really that communicates, any data in transit, anything that communicates on IP, internet protocol, anything that uses TLS as a transport layer, anything that uses SSH to sign in as a secure layer onto a device, virtual private networks, digital signatures, authentication of a server to another device. All of this is threatened by decryption because all of these methods that we commonly use every day use an encryption layer around them. To protect the network, to protect the device, to protect the login on the machine. And so the threat is very ubiquitous. It travels from everything from your very, very largest, excuse me, your very largest data center firewalls, let's say, in a data center, all the way down to an IoT beacon that wants to transmit and backhaul its data. Thanks, Steve. So estimates range, it hasn't arrived yet. So opinions always have a range, nice Gaussian distribution range generally. So the left-hand side of the Gaussian curve starts at something like 2028, 29, and the right-hand side kind of sensibly ends at about 2037, 38, 39. So the threat is in the future. So we don't really need to take it seriously today, do we? Well, yes, we do. The threat does become serious today. And in the networking world, the biggest threat currently is something called a harvest data now, decrypt data later attack. And it simply means if I middleman a data stream and I interpret it, even if today it is encrypted with a RSA or one of the common encryption methods, in the future I can take that data stream, I can pass it back through a quantum computer, decrypt it, and then I can read the plain text version of what I thought was protected by a lifetime ciphertext. And this is one of the main reasons now why businesses and companies, particularly on networking, are taking this very seriously. Now, let's go back to these dates. So IonQ is one of the leading companies that's developing quantum computers. It's listed on the NASDAQ. It has to make sensible announcements to the NASDAQ stock exchange. They've sent that on one of these sensible announcements, they've said that they think they can break encryption by about 2029. Might be 2030, but that's the date they've put out there. In terms of investment and money, there's a lot of money going in from the Americans. There's a lot of money in Europe, not quite as much, but there is. Japan, Singapore, Australia. If you look at the news flow that is around quantum computing, you can see that there's vast billions of dollars of research funding and development funding going into developing these quantum computers. And just to underline that, that's only half of the world's spending, because the rest of the world's spending comes from China, and they've been quite open about showing the West how much money they're applying to this particular issue. And just to underline this, final bit on the slide, the UK government did not announce we had decoded the German Enigma machine until 1975. And why would we? Going back to the China comment or other bad actor threats, why would anybody tell us they'd actually finally decrypted the RSA or ECC or any other encryption method? Why would they announce it to us if they didn't want to tell us that fact? Thanks, Steve. So this is the Gaussian time curve that I was talking about. So down in the bottom left hand of this slide, there's a star, and it has Shor's algorithm. This is a gentleman called Peter Shor, who was a kind of mathematical physicist, and he made calculations based on putting a 0 and a 1 into the same memory space on a computer, that sometime in the distant future, 2060, 2070, it may be possible for a theoretical quantum computer to break the encryption methods that were being used at the time. And NIST started to take this seriously, the National Institute of Science and Technology in the USA, and they had a competition that they started in 2016, which ran for 8 years, I think I should say. And as a result of that competition, this window kind of came in as the technology started to develop. And their competition was, let's find a harder maths problem than the current ones we're using, so that these quantum computers won't be able to break these harder maths problems. And that's been confirmed recently by McKinsey. They published a paper in 2024 where they brought all of this forward again. Their guesstimate, these are all guesstimates, was somewhere between 2030 and 2040, this becomes a real issue. And then last summer, when we were presenting actually to a large data center company, global one, on the day, I think it was 23rd of June 2025, up popped this announcement from IonQ or Ionic, depending on how you want to pronounce it, that they would have by 2029 8,000 logical qubits in a memory space, and that's enough to start breaking up these common encryption methods that we're using. If you move on, please, Steve. So look down at the little blue rectangular box at the bottom. This counts up the number of logical qubits using Peter Shor's theoretical mathematical physics. How many logical qubits do I need to start to break open these commonly used algorithms on a quantum computer? And we can see that the longer the key length, the more memory it occupies, the more logical qubits are required. So make your keys longer and it becomes a harder maths problem. There's an echo of that back in TLS and AES, because AES doubled its whole length, well, doubled it in terms of power, from 128 bits to 256 bits. Some people might remember when it was AES 128, not AES 256. And so this ECC and RSA maths problems, algorithms, they are based on they're based on basically key factorization, and they're also based on logarithmic curve. And these apparently, don't ask me to do the maths, but apparently they're quite trivial for a quantum computer to break open. So that endangers PKI, it endangers any digital certificates you're using for authentication. The handshake in the middle of AES, that actually, funnily enough, uses the same encryption currently, and that's starting to be replaced now by post-quantum methods such as CHEM. And the NIST set of responses to these weaker maths problems are harder maths problems. That's what NIST now calls its post-quantum cryptography set. And these for now are called quantum resistant by NIST. I'm just saying they've just used the word resistant, not quantum safe forever. Okay, thank you. Okay, so the primary response to having an easy to break up or easy to solve, let's say, maths problem algorithm is to make a harder to solve maths problem. And there's a lot of work being undertaken in this cryptography space where we have things like called one-way problems, for example, where if you input the number, you cannot reverse the mathematics of it. You can't unpick it. Now, That's not very good if you want to decrypt something, of course. It's actually quite useless. But there are mathematical algorithms and problems that can solve and make the mathematics more difficult for the quantum computers to break. One of the ones that is commonly being used is the chem method, which is a multiple vector layered maths problem. And that is often given the name as a crystal because it's like a crystal lattice. It's different layers of layers and layers upon layers. And the output of that is not easily reversible as it is for RSA, which is just based on prime factorization of very large numbers. So for now, NIST and lots of other organizations globally have recommended using these approved encryption methods. But they're harder maths, they use a lot more computational power, and they use more memory space. Now, if I'm running a data center, I don't really mind, but I do mind if I'm running an IoT device. Okay. The other alternative to using asymmetric encryption is to use symmetric encryption. A bit like AES, which protects data in transport, it uses symmetric keys. It doesn't share the key material in a PKI structure by passing it down the data channel. And the more key information you can keep away from the data channel by using a symmetric key method, the better. Okay, Steve? Right, I'll hand back to Chris there. We've undertaken our high-level introduction to quantum computing and the response of the encryption layers.
Thank you very much indeed, Richard Brooks of Blue Mesh Solutions. So, if you go to the news section of the IoTSF website and scroll down a bit, you'll see a superb opinion piece by the IoTSF's John Moore, all about what we're calling SBD3, excuse me, which is security by default, security by design, and security by demand. If you're watching this broadcast live, the link for that opinion piece is in Zoom chat right now. So both of today's webinar guests are leaders of the IoTSF Quantum Safe IoT Special Interest Group. The next meeting will take place on Tuesday, the 3rd of March. And if you're not already involved, you can get in touch with me. It's chris.bennison@iotsecurityfoundation.org, and we can get you along to the next meeting of the Quantum Safe IoT Special Interest Group. So that was just a short little break in the middle. We now continue with today's Quantum Safety Special. Up next is Stephen Kennedy. If you have any questions on what you've been seeing today from Richard, or any questions, comments, observations about what you're going to see from Stephen Kennedy, please put them in Zoom chat. Steve, the floor is yours, my friend.
Thank you very much, Chris. And thank you, Richard, for the great introduction to quantum computing there. I am going to talk more about the actual implications for IoT. So I think Richard gave a good overview, but what does it really mean for IoT devices? So let's start off by considering the quantum threats for IoT. Harvest now, decrypt later is the classic threat that is being publicized across the board whenever anybody talks about post-quantum cryptography and the risk from quantum computers. And that is the ability for a bad actor to store off your data that is 100% encrypted today and wait until they have the capabilities to decrypt that data. I failed in Presenter 101 by asking if you could see the slides, so let's try again. How is that, Chris?
There you go, Stephen.
Fantastic, thank you. So yeah, the harvest now, decrypt later is a classic threat from quantum computers, and it applies to any data that you need to keep confidential for the next 5, 10, 20 years. So maybe not all IoT devices produce data like that, but I'm sure that every company producing IoT devices does have data of that type. And a lot of the data that might be transferred from industrial sensors, etc., could be a trade secret that you don't want your competition to have access to, even in 5 or 10 years, as it could jeopardize any competitive advantage that you have. So definitely to be cognizant of the harvest now, decrypt later attack. And then there's a whole bunch of other threats that are related to just breaking the authentication on the device or gaining access and control of the device. Obviously, there's been a long history of IoT devices being used as zombies in DDoS botnets, and that could come roaring back if the security measures in place could be cracked by quantum computers. Um, and yeah, you could easily lose control of the device, have malware installed on it, and the device could be spoofed if the quantum cryptography, if the quantum computer can break the cryptography and present itself as the device back to the core network. Also need to be concerned about lateral movement onwards from an IoT device, which maybe is at the edge of your network, but we've often seen in real attacks, the attacker creates a beachhead and then they have ample time to explore the rest of your network from the inside and work out the best way to increase the attack effectiveness and cause you more trouble. Okay, and then switching gears from the potential threats to IoT devices from quantum computers, let's also consider the legislative and regulatory landscape. So while Richard was very correct that there's an ongoing debate as to when quantum computers will be developed that can break the existing encryption ciphers, one thing that is pretty clear across the board is that regulators and legislative bodies are introducing legislation, regulation that will enforce a move towards quantum safe ciphers. It's happening across the board. Pretty much every country you look at is investigating this and bringing something into law. Typically, the magic date is 2030, as has been defined by NIST, and everybody else is following that. And by 2030, the vulnerable algorithms will be deprecated, and you really do need to have quantum safe versions implemented by then. And then just drilling down into what's happening in the United Kingdom, as you may have guessed from my accent, it's where I call home. The UK Parliament is passing the Cybersecurity and Resiliency Bill, which should go into law in 2026. That bill references the CAF, the Cyber Assessment Framework that's been produced by UK's NCSC, which takes the slightly cryptic legalese of a bill through Parliament and puts it into a much clearer architectural context for engineers to follow to ensure they have good compliance with the bill. Cryptography is mentioned several times. As an example, I've pulled out the data in transit section here, where you can clearly see if you don't have good knowledge of your cryptographic estate and the ciphers that you're using, or you've identified them and they have weaknesses, then you're not going to be compliant with legislation. It's important to have a very good knowledge of the cryptography that's been used in your estate and to ensure that that cryptography uses appropriately secure ciphers to protect your data. And while this bill is fairly generic, applies across the board, my understanding is that individual regulatory bodies for different industry verticals are going to use it as a basis for their own regulation. So this should give you a preview of what's going to come down the line from your own specific regulator if you are an IoT vendor or deploy IoT devices in a specific vertical. Um, Now, switching gears again to look at the actual post-quantum cryptography ciphers that have been developed. Um, from the perspective of the UK and the US, the NIST is driving the cipher development here. I believe Korea and China are also investigating their own parallel models, but it's going to be a very similar pattern. And specifically, the ciphers that are based on the difficulty of breaking down a product of two large primes into its prime factors um, are the ciphers that are being deprecated. So that's RSA and ECDHE, as well as other equivalent digital signature algorithms. And in order to replace those ciphers, NIST has developed four new ciphers. Well, three have been standardized. Falcon is expected any day now. It's just been delayed by US government shutdown of funding. And this table demonstrates that we go from the more interesting some Star Trek themed names such as dilithium down to MLChem and MLDSA, SLHDSA, etc. But the problem is these standardized ciphers have been designed for the general use case for devices that have significant CPU resource, significant memory, are operating in networks with high bandwidth, good latency, etc., etc. If we consider the more difficult IoT use cases that are out there in terms of memory constraints or network constraints, then it's not necessarily true that the standardized ciphers are going to be a good fit for those devices. Here's a comparison table I pulled together on the digital signature algorithms, and you can see there's a big range in terms of what they offer. MLDSA has been developed as the mainline cipher that satisfies the majority of use cases. But then SLHDSA has been developed as a cipher that has a smaller memory footprint, but requires more CPU cycles to use. And Falcon has much smaller key size and memory requirements, but it's very computationally expensive to actually generate the keys. So when you are developing new products or asking vendors questions in RFPs, you need to apply more focus to the actual attributes of the cryptographic ciphers that have been used in the devices in order to have a high degree of confidence that the devices you're getting are going to be a good fit for your use case. I think previously cryptography was regarded as something that just worked and didn't need a lot of due diligence during the purchase cycles. And as we move forwards into the post-quantum cryptography world, it's going to be important to apply an additional degree of scrutiny to the actual ciphers that are being used and the underlying performance and memory requirements of the algorithms. And likewise, in terms of key exchange mechanisms to replace RSA or Diffie-Hellman, MLChem is going to be the mainline cipher that replaces those. There's another cipher that could be standardized in the next 2 years or so to provide additional cryptographic diversity. I don't think it's 100% clear yet on whether MLChem will be acceptable for all IoT use cases that are currently use the previous generation of ciphers. But again, focus needs to be applied to this area to make sure that good decisions are made moving forwards. So what should you do in terms of something more concrete? So at Blue Mesh, we've developed a system that we're calling CURD, cryptographic orientation development exercise. And CURD is a framework that lets you develop your quantum safe strategy. So the first step is to get a really solid understanding of all of the places where you're using cryptography in your estate today. So there's cryptographic tools available in order to discover all the places you're using cryptography, and building out that understanding, the C-BOM, the cryptographic bill of materials, that will help you then design a strategy and a plan to replace the vulnerable ciphers that you have in your company today with their quantum safe equivalents. And then undoubtedly following the initial discovery exercise, there'll be some easy, quick wins. It's very clear that you can do a quick replacement with a new cipher that's secure, and good to pick off those quick wins in order to minimize your exposure as quickly as possible. But it's also important to bear in mind there's going to be a lot of hard yards in terms of working with vendors to get quantum safety onto their roadmaps, difficulties in terms of upgrading hardware devices that might be in the field. A lot of enterprises have that old IBM server that's been sitting in the corner for 20 years with a post-it note on it saying, do not touch, do not switch off. What are you going to do about that? So plenty of tricky problems are going to be exposed as part of this move from the old cryptography to the new quantum safe cryptography. So 5 years may seem like a long way away, but it's going to move pretty quickly as you look into the actual length of time required to address some of these issues. Okay, so just to summarize what we'd want you to take away from this presentation, the quantum threat to IoT is real. Post-quantum cryptography is here to mitigate that risk. IoT solutions are likely to require specific PQC algorithms for specific use cases, some of which may not be standardized by NIST yet. There is work underway in many different bodies to enhance the IoT communications protocols and the ciphers, so you're not alone. And one critical factor for IoT deployments, especially sensors, industrial IoT, things of that nature, is that they may be deployed with a long lifetime, and they may be more difficult to upgrade than standard software running in servers in a rack center somewhere. So what we think you should do about it is conduct a comprehensive risk assessment as soon as possible. Don't underestimate the length of time it will take to replace these devices with long life cycles. Keep abreast of those developments in standards bodies and the wider industry so that you can leverage the knowledge that's out there, and keep reviewing those standards and protocols to stay abreast of what current best practices. And then finally, adopt post-quantum cryptography, and then also keep an eye out for crypto agility, which basically means that we may deploy a post-quantum cipher today that is currently not cracked, but with the advances in quantum information theory and quantum cryptography, even the new ciphers may become susceptible to different types of attacks. So Shor's algorithm 2.0 in effect. And when they do, you're going to want to be able to switch out the old cipher for the new cipher in a much more streamlined and simple way than is likely to happen with this first exercise to replace the current generation of ciphers. Okay, and with that, we'll open the floor to questions if there are any, Chris.
Thank you very much indeed, Steve. We'll get to the Q&A section of today's broadcast in a few moments, but before that, I'd like to tell you about our March 2026 webinar. We'll have Johnny Tyers of ThreatPlane presenting Standards versus Security, a proactive compliance framework. We'll also have Murat Çakmak of Zaya with autonomous compliance, operationalizing EU CRA and UK PSTI via embedded microservices. If you're watching this broadcast live today, the link to register for that one is in Zoom chat right now. So onwards with the Q&A, and this first question that has come in has a lot of esoteric terminology in it. So I hope everybody is about to understand what I'm going to say. I'm probably mispronouncing a lot of terminology here. This is from Trevor. I think this is more of a comment stroke observation than a question. AFAIKAES is not really vulnerable to PQC. The algorithm is not based on factorization. However, the wrappers for exchanging the key are. This means pre-shared keys are not vulnerable but have other problems. I can see that you've just clarified this as the asymmetric algorithm is the bit, that's the bit that is vulnerable. Richard, I'll bring you in. What's your response to Trevor's observation there?
Well, Trevor's absolutely right. Well done, Trevor.
Trevor normally is.
Of course, what I was referring to was the handshake initialization, which has used an ephemeral RSA, I believe, in its structure, and that's the part of the AES that is at risk. Once the symmetric keys are established on the endpoints, then hopefully that symmetric key agreement between the two endpoints is actually not at risk, but it's the initialization, the handshake, as people commonly call it, that's the risky part.
All right, thank you very much. Stephen, have you got any reaction to that? Anything to add?
Yeah, I think just it could be a question of terminology here as well. I think in the standards bodies, AES is of course the symmetric cipher that's used within the TLS exchange or other types of exchange. But in a lot of industrial contexts, AES is used interchangeably with TLS. So that's perhaps standardization versus sometimes a bit of looser language in practice.
Okay, thank you. I'll put this one to both of you. Where has my questions gone? Bear with me. This technology, is it actually ready and deployable? Richard, I'll come at you first.
Is it ready and deployable? Well, I kind of yes and no. Sorry about that answer. So as Steve has pointed out, and maybe Trevor's pointed out on the chat as well, a lot of this isn't tested. A lot of the kind of real world workings of it, like memory allocation, etc., hasn't really been given a huge amount of focus. You can go to a crypto library now, say libQoS, which was the old IBM library, and that will contain the calls that you need to call these algorithms. At the bigger end of encryption, the large firewall manufacturers are now starting to deploy. They're starting to deploy quantum key distribution on the firewall ends, and on these lighter ends, the IoT ends, we're seeing some algorithm methods now, with one of our technology partners, actually, to be fair, Quantropy, where they have much lighter, more efficient algorithms, but with the same type of permutation space, and but they're not yet certificated or registered. So yeah, it's still developing. It's a yes and a no. My answer to that. Sorry, that's a bit vague, but yes.
That's all right.
Yes and no.
Maybe Steve can expand.
Yeah, I think it depends where you are in the value chain as well as to whether these solutions are already available for you to take and use. So if you're a software vendor looking to define your roadmap, then now is a good time to look out to what's happening with OpenSSL or whatever third-party library you're using for encryption, and to get a new version so you have access to the new ciphers at the point that you want to upgrade your solution. And we've seen with some of the big guys like Cloudflare and Google, I think Google have implemented updates to their boring SSL, that's their name, for their version of OpenSSL that they forked themselves a while ago. That includes all the quantum safe stuff, and they've just enabled it because they control the full stack, so that is within their purview to do. But if you are sort of an end customer deploying IoT devices, and you buy your device from a hardware vendor that gets the software from another vendor, then it may take multiple releases for that to percolate down the supply chain where you're actually in a position to deploy a quantum safe cipher yourself. So yeah, I think the key to whether this is already deployable or not is where you are in that supply chain. And if you're an end customer who's buying a lot of equipment that uses cryptography, then get the conversation started early with your suppliers to check they're having the conversation with their suppliers to check that it's all going back to whatever the mathematicians are doing with NIST, etc.
Thank you very much. One other observation from Trevor that I do want to read out because I think it's pertinent. You have to be careful of the reference code for for the DSAs, as Stephen showed metrics from these. As the code has not been hardened, and there is research showing these are a bit leaky to side channels, etc. This means the code is likely to be more complex and possibly less prominent than shown. Richard, what's your reaction to that?
Yeah, well, again, I agree. I mean, the protection of memory, again, is a big issue, and until these algorithms have been run on different memory devices, then to be honest, they're probably haven't been properly soak tested. I would also add that I believe ARM at the moment are making a vault area inside their processor so that a part of the operating system can be vaulted away so that at least it can't be side channel attacked. And I think they're coming up with that quite soon. So that's some development work that's taking place. And I imagine if you're going to be running an RTOS and the ARM vault would contain maybe some signature identification, authentication areas, and you would post quantum protect those as well, because then you've kind of got two locks on your stable door. So yeah, again, I agree.
Okay, Stephen, anything to add on that one?
Yeah, definitely the main emphasis of those slides wasn't to say, okay, you're making a purchase decision, this is the performance characteristic you're going to get out of the cipher. It was to highlight there's a wide range of different performance characteristics for the new ciphers, and therefore this is an area of concern that you need to start thinking about more than you used to. I think I took the data from the benchmarking by libqs. So yeah, however that gets implemented, or even if a different library is used, then the performance metrics will be different. But the key is that it's going to become important moving forward, so you need to pay attention to it. So I think we're all in agreement there with Trevor.
Nice one. This next question is from Richard. Richard works for a telecom company that everybody has heard of, so this question should be no surprise from him. Richard asks, as well as the 5G private network tests, did you also test on LPWA technologies? If so, what observations were taken?
Right. Well, unfortunately, we can't really answer that in any positive way because two things happened, Richard. One, the project timeline ran out, basically. So some of the further extensive work that we had planned for didn't actually take place, and the other point really is that I think we got much more drawn down by the engineers on the Port of Felix, though, once we got the project up and running, into focusing very much on the digital twin part of the project. Now, I know this started off as a standalone network, 5G network funded project, but as the thing developed and as the engineers started to see the digital twin emerging from Trinity College's great work at Cambridge, that started to get a lot more focus and attention by the engineering team at the port. So yeah, yes, we didn't go down deep into testing it on NB-IoT, etc. At the time, purely because that's just the way that the project pivoted a little bit in the other direction.
Stephen, anything to add on that one?
Oh, that was before my time at Blumesh, so I will defer to Richard for that.
He was still working at Microsoft then, I think.
Okay.
Yeah.
By the way, Trevor, just one final thing from him. He says, thank you both. I just wanted to clarify, not poke holes, but great presentation. Trevor is the politest gentleman in all the world, but we are not here for the easy questions, are we? So thank you very much, Trevor. Let's go to Ranga. Why does the PQC concern always get positioned as HNDL? Is it not far more dangerous to have the signatures broken? What I have seen referenced as trust now, forget later. Not all our messaging needs confidentiality, but all exchanges need trust between parties, do they not?
Yeah, it's a fair point. I think from my stance here, reading it, I agree. There is quite a lot of focus on the harvest now, decrypt later threat. That's probably because a lot of the actual deployment of this is going on in firewalls, which protect things like banks and financial services and insurers, data centers. And if I'm running an insurance company, I'm probably more concerned about harvest now, decrypt later, because I've got information on that data pipe that's going to probably still have value in 5 or 6 years' time. And the large firewall manufacturers like Palo Alto, Juniper, Fortinet, Cisco, etc., they're now switching on PQC to connect firewall to firewall or firewall VPN, and they're out there making a lot of noise about it because they've got big marketing budgets and that's what they're selling. So it's a bit of a case of give the people what they want. I think that's why the threat is so widely discussed.
Ranga's just clarified. It was a typo in what I read out. It was meant to say trust now, forge later. So that's not messed up or derailed the context of the question. With that in mind, Stephen, trust now, forge later. Discuss.
Yeah, it's certainly got to be a concern. I think that it's probably just conceptually easier for non-experts to understand that you've got something that's secret, and at some future point, somebody you don't want to read it will be able to read it. Whereas a sort of attack that involves forgery at some future time, I think that just is a little bit conceptually harder for the non-expert to get their head around. But yeah, I could imagine you've got DocuSign documents, etc., etc., and then at some future point, when a quantum computer can break the authentication, suddenly you get a load of documents appearing that appear to have been from a user that just not true. And I guess there's going to be comparisons with sort of deep fake videos and things of that nature. Today, they can be authenticated with the public key of whoever purports to own the video. As soon as a quantum computer comes along that can break that, then suddenly all of the videos that you see could no longer be trusted to be from the people that they claim to be from, which is going to be a significant issue. I would also say that probably that's more obvious that it's happened. And if there's a massive tsunami of loads of forged content appearing, then that's a strong indication that someone's got a quantum computer that can break cryptography. And I think the general consensus is the threat actors that are going to develop that quantum computer initially are not going to be broadcasting the fact they've got it, because they're going to want to be using it without people being suspicious. So, but again, if they could just forge one or two things that are very impactful, then that could be a big problem.
Yeah, we've got Holyrood elections in Scotland coming up very soon. I wonder if that sort of thing is going to play a part in it, probably in future general elections and referenda as well. Tatiana asks or comments, how will PQC handle such a thing? They barely run half of memory, and crash upon a single map scan. Expecting them to handle even half beaded step is my misunderstanding. I hope I've read that verbatim. Richard and Steve, can you see that question?
Yeah, and I think Tatiana's added Arcit VPN as well at the bottom of it. So I might have to guess what she's referring to here slightly, but I think potentially it's the something standard called RFC 8784, which is for the key sharing 2 method internet key exchange. That's using the NIST PQC inside that method. And as I said before, some of the larger companies like Paolo, etc., have updated their operating system to operate the RFC 8784 method as well. Coming back down to the smaller devices again. So this is an issue that the smaller devices without the memory space, without the compute, which large devices have, they're memory constrained and they're power constrained. Now, we're going to invite on a company called Quantropy in a couple of special interest group time, because they have a very lightweight approach to this. They've got their own novel algorithms, and we being Bluemesh, we've taken one of their algorithms, one of their lightweight algorithms, and we've used that to create a quantum safe MQTT data broker based on the Mosquito data broker. And we'll be showing and telling that quite soon. That's the type of direction I think for restrained memory and restrained devices that, and I think Tatiana's saying there's too much payload, too much memory. These lighter weight encryption methods, which aren't yet but will be NIST approved, I think they'll solve a lot of these issues. And just to say, ST Micro has just taken up this technology to put on their sensors, as have Renesas as well. So it's an emerging approach, and I think it's valid to bring to the group and demonstrate it with Quantropy.
Stephen, any addition to that?
No, I think Richard covered it really well there. It's a tricky problem. I'd suggest engaging with experts, joining the IoTSF special interest group. It's a good place to find those experts.
Tatiana clarified again, this is esoteric language, so I'm not sure if I'm reading this out correct. Arquit VPN, she did mean PLC, not PQC. PLC handles the payload or paycode with new regulations, and Arquit VPN about readiness brilliancy. It's PLC for basic critical infrastructures. Have I just made myself sound silly, or does that make sense?
I think is PLC programmable logic controller in low-level industrial processes.
If you clarify that, Tatiana, that would be.
I think Tatiana might be referring to the integration onto the. Are you referring to the integration that Arquit have done onto the Intel board, Tatiana? Yeah.
PLC in OTA ICS.
Yeah, it's operational technology. Yeah.
Yeah. Okay. Yeah, I think that's a great topic to bring up in the SIG, and if you join Tatiana, then we can have a message board on it and see what people think.
Yeah, come along to the SIG, Tatiana. We'll do this in a bit more detail.
Yeah, when did I say the next meeting was? Was it March? I've got to
March the 3rd.
Yes, that's Tuesday, 3rd of March is when the next Quantum Safe IoT Special Interest Group meeting is going to be. It's for IoTSF members only. I should clarify the details are on our members only platform, as is the meeting link for that. But if you do want to get involved, just drop me an email. It's chris.benison@iotsecurityfoundation.org. We've only got 1 minute left. Trevor, I love it when people are this engaged and into the broadcast. Trevor, let's finish with Trevor. One last comment from Trevor. The risk analysis that everyone should be doing will help in identifying what data is sensitive to long-term security. Some data, example, sensor readings of continuous time information, temperature, rainfall, or similar, does not really have to be protected long term, is more sensitive to real-time tampering. Again, a comment, not a question. How would you quickly like to react to that one, both, before we have to head off?
Well, I agree. I mean, if you turn on the radio, they read out the temperature every day, on every hour, on every news item. So it's not the type of information that needs to be protected. If the data that you're back calling has a very short life, if it's only important for 1 minute, then harvest now, decrypt later isn't relevant. But does the device become an attack surface? And of course, that's the next layer of questioning that you need to ask yourself.
All right, Steve, one final word from you.
No, I think Richard summarized it well. If somebody wants to take the historical records of my Nest thermostat to see that I don't turn on the heating in winter because I'm too tight and I just put a jumper on, then c'est la vie, they can have it.
All right, one final comment. Steve, Seal SQ has released a PQC-enabled MCU and will be releasing a PQC TPM and SE. Thank you very much for that, Steve. We are out of time, I'm afraid. I'm so grateful to yourself, Richard, and to yourself, Steve, both the leaders of the IoTSF Quantum Safe IoT Special Interest Group. As I've mentioned, if you want to get involved, please do join us on their next meeting, which will be online. I'll Repeat once more, next month's webinar, we're going to have Johnny Tires of Threatplane presenting standards versus security, a proactive compliance framework. We'll also have Murat Chakmak of Zaya with autonomous compliance, operationalizing EU CRA and UK PSTI via embedded microservices. If you're watching this live, the link to register for that one is in Zoom chat right now. Open it up and open it up in a new tab right now before we finish on Zoom and everything disappears. Thank you very much for joining us today. Thank you again to Stephen and Richard of Blue Mesh, and we'll see you next time.